The second law of thermodynamics is everywhere in our world. Whether it's eating a food, popping a balloon, cleaning up your room, or walking around the school, the second law of thermodynamics is everywhere in our world. Basically, it states that any time energy is transferred between objects or transformed from one type of energy to another, some of the energy is always converted to thermal energy. So what does this mean? This video will entirely focus on explaining this concept. Here, as the metal ball hits the other ball, the energy is transferred. However, the cradle eventually comes to a stop as the energy consistently gets converted to the thermal energy. Let's look at this from a different perspective. Fast forward. Finally, the cradle is coming to a stop as most of the energy was converted to the thermal energy. We now understand the concept of the second law of thermodynamics. Now it's time to link the idea of entropy with the concept of second law of thermodynamics. First of all, what is entropy? Basically, entropy means disorder. So in terms of entropy, we can say either the entropy is high or entropy is low. Let's look at some examples. This room has high entropy because this room is very messy, while this room has low entropy because the room is very clean. Now that we know the second law of thermodynamics and entropy, let's link them together. So the thermal energy plays a huge part in the second law of thermodynamics. Basically, as the energy is transferred between objects, some of the energy is always converted to thermal energy. Now, that thermal energy, we can say that they are random atomic motion, because there are definitely oxygens, even right here in my hand. There are oxygen atoms, hydrogen atoms, and there are many atoms in my hand. And as the energy moves out as the thermal energy, these random atomic motions increase and the randomness increases because originally they were confined in this very organized fashion until the thermal energy kicks in. Therefore, thermal energy creates this random atomic motion, and such random atomic motion creates randomness that causes order, that causes an increase in entropy. Alright, back to Newton's cradle. Remember I told you that there are so many molecules in the air, including oxygen atom, hydrogen atom, and so on. Before I let go of the ball, the air surrounding the Newton's cradle is very organized. However, as soon as I let it go, and thermal energy is released, the entropy will increase. Furthermore, as the thermal energy gets radiated out from the Newton's cradle, and as the air molecules collide with each other, the entropy of the surrounding air will increase even more as the time goes. Now, here it is important to realize that entropy will always increase over time, unless the work is inputted. That's a different story we'll talk about later. So, just like we cannot absorb back the thermal energy that has been already released, entropy cannot get decreased over time. Look at this video. Is it possible for an object to slowly increase its energy as the time goes? No, it's not. Alright, let's look at this other clip. The water is slowly coming back to his hand. Coming back, condensing, and then regains order. Alright, using common sense. Is that possible? No. You might have guessed, but we used the reverse effect on iMovie to show both examples. That just basically means that if the entropy decreases over time, or the randomness or the chaosness decreases over time, that means the time is not flowing the right way. Time is flowing backwards. But now here's the question. What if the entropy stays the same? Here in this freeze frame, you don't know for sure if the time is flowing backwards or flowing the right way. Therefore, can you tell me if the entropy is increasing or decreasing? So give me an answer. Is the entropy increasing or is the entropy decreasing? Basically, As I've shown by two previous examples, if the entropy does not show any change, then we don't know if the time is flowing forward or backwards. Now let's talk about a different concept, or the concept that we talked about previously, that we said that entropy cannot be reduced over time. However, if the work is inputted to the system, then the entropy can be reduced. Let's look at this example. As the papers here are getting organized, it is moving from the state of high entropy to low entropy. And how is it possible? It's because Jake is putting work into it. So now let's review the concept that we learned. Entropy will always increase over time. It cannot be reduced unless work is put into the system. Now let's move on to our final concept. By linking the ideas that we learned previously, thermal energy and potential energy, and link it to the ideas that we learned now, the second law of thermodynamics. Alright, let's go back to Newton's cradle. By doing this, I just increase the potential energy. However, even though I increase the potential energy, that does not mean that I increase the entropy of the system. The entropy of the system stays the same. It's relatively low, because the air molecules surrounding all the Newton's cradle, or the balls here, it's pretty stabilized. However, if I release it and release the thermal energy and releasing the kinetic energy, the entropy will increase, just like we learned previously. So basically, we can now see that the potential energy is a state of low entropy because the energy is yet to be released, and the thermal energy that will disrupt the air molecules surrounding it has not been released yet. However, the thermal energy is the state of high entropy because the energy is already radiating out of the system that will disrupt the system surrounding it. So that was everything about the second law of thermodynamics. Thank you for watching the video.